All right, so I want to show you two more useful limit rules that won't surprise you but are good to know. So the first one is the limit as x goes to a. I've got a function and I'm raising it to some power. Then you can do exactly what you think you can do. You should write this, you can write this as the limit as x goes to a of f of x all to the nth power. You can pass the limit inside the power. And similarly, if you have an nth root, this actually applies if the power is a fractional power. You can write this as the nth root of the limit as x goes to a of f of x. And so I think these laws are best understood through an example. So let's go ahead and do one. We'll look at the limit as x goes to 2 of the square root of x to the fourth minus 12. And right away I recognize that, oh, look, this square root is a second root, if you will. And so I can write this as the limit, as the square root of the limit as x goes to 2 of x to the fourth minus 12. When I want to evaluate this limit on the inside, I know that, oh, that's a polynomial. Its domain is everything, so I can just use the direct substitution property, and I get, of course, 2 to the fourth is 16 minus 12 is 4, so I get root 4, which is just 2. So there's the first limit. Let's slide up this example for a little bit more space here. So second limit, second example, limit as x goes to 0 of sine of x. Sine of x is just a trig function. Its domain is everything. So I can just use the direct substitution property and realize that the limit is going to be the same thing as the sine of 0, which we know is just 0. And then finally, I wanted to do another example with you. Let me scoot this one up as well. So I want to take the limit as x goes to 2 of this function, and the function is piecewise defined. So let's see if we can sketch a picture of what's going on with this function to help us understand. So we'll begin by just sketching this part. So this is a line, 3x plus 2. So it has what? Y-intercept 2 and slope 3. So out 1 and then up 3. And so I can go ahead and graph this guy. And now the catch is, whoops, we need to go down. There we go. Close enough. A little bit off there. The catch is there's actually a hole at 2. Let me slide the whole picture down. We're getting into my, whoops, my squiggly bracket got caught there. There we go. So it keeps going like that. There's a hole at 2. And so let's think about what the value of this hole is. Well, the value of the hole is what you would get if you plug 2 into this, which would be 8. So this is sitting right here at 8. This line is y equals 8. But this function is not equal to 8 at 2. It's equal to root 10 at 2. And you know that root 10 is a lot less than 8. And so, because root 9 is 3. So this is a little bit above 3. So somewhere down here there's a dot. So that's what it looks like. And whether or not you draw this out and you see it and you say, okay, look, the value of g at 2 is root 10, but the limit that g of x is approaching as x goes to 2 is actually just this y value 8. You can do that and say, therefore, the answer is 8. You can look at the picture and see it, or you can recognize that these functions, this function g of x, is actually just equal to the function f of x equals 3x plus 2, right? It's equal to that function except at this point. And so you know that the limit at that point is going to be the same. So any way you think about it, the limit is just 8. You get 8 because that's what the function g is getting closer and closer to. You can just ignore this line using the property that we talked about above. All right, so let's stop this video here, and then we will look at some more limits in the next one.